Welcome to problem solving. All right, we're going to look at Polya's problem solving process and then how to apply it to solve various types of word problems. Polya developed a four-step problem solving process quite a while ago, and most people use it or use some sort of version of it when solving word problems or teaching others how to solve word problems. Step one is he wants you to understand the problem, which really means just read it through and look for some important details. Step two is to develop a plan and figure out, what works best for this particular problem. Here are a bunch of examples of the types of things you could use. Step three is, of course, to carry out the plan, and step four is to look back and make sure that everything worked and that your answer is logical and feasible. Let's look at one example that uses working backwards. So you've got three watchmen that are guarding an orchard. A thief slips in, steals some apples. On his way out, the thief is met by each of the three watchmen, one at a time. And at each watchman, he turns over half of his apples and then two more. So he gives him half of what he has, and he gives him two more, and then he moves on, and then he bumps into the next guy. Oh, darn. Gives him half of what he has, two more, and then moves on, bumps into the third guy. And after he does that three times, he escapes with only one apple. And the question is, how many apples had he stolen originally? Well, if we go back and look at the develop a plan slide, these are kind of the different tools that we have in our toolbox when we're trying to solve word problems. And the hardest thing for solving word problems for students is not developing a good toolbox and not knowing how all of these tools work and when to use which one and all that kind of stuff. Because once you get a strong set of tools, you can tackle all word problems, because most word problems kind of land in a very small number of sets. You'll have a whole bunch of word problems that all are grouped together as being distance equals rate times time problems. Problems that always deal with something moving in a certain direction at a certain rate for a certain amount of time. Like Joe drives east for 20 miles, then turns and drives north for 30 miles. How far is he from where he started? Two trains are traveling towards each other, one at 20, one at 35. How long until they collide, right? All these different types of questions are all dealing with distance equals rate times time. And when you recognize that, you know that you solve them all using distance equals rate times time. Then you have a whole family of questions that are all mixture problems, where you've got 20 milliliters of an acid and 100 milliliters of a base. And how many do you have to mix together to have a 50 milliliter solution that's 50% acid and 50% base? That kind of stuff. Or you've got 2 pounds of peanuts and 6 pounds of M&Ms. How many of each do you have to put together to have a trail mix that's 3 pounds, that's 30% M&Ms? Those are mixture problems. So once you start noticing kind of patterns, then you know that they're all mixture problems are solved a certain way. All distance equals rate times time questions are solved the same way. All geometry questions, questions that involve geometric figures like a square, a rectangle, or a circle. Like a ladder's leaning against a building and it's sliding down and blah, blah, blah. Or you have to put a square fence around your plot of land. Or, you've got a plot of land and there's a river on one side and you want to make a rectangular pen on the other three and you've got this much fencing. All of those things are what I call geometry questions. So they all deal with, knowing what's the perimeter of a circle or the perimeter of a rectangle, and what's the area of a rectangle and the area of a circle, and all those kind of geometric formula questions, right? So some of these techniques, working backwards, drawing a picture, guessing and testing, work better with some questions, and some don't work so great with some questions. You just got to kind of figure out which ones work best. Sometimes you try one, it doesn't work, and you move on, you try another one. All right, let's go back to our question of the apples. And even if we didn't have the wording up there telling you that example one is a working backwards example, you might think that that would be a good technique because they tell you how many he has at the end, and you know that you have to work backwards to figure out how many he started with. All right, so it's a working backwards example. So after reading the question and realizing that we're going to work backwards, well, then you realize that you have to unfold everything that he does. He gives them half and then gives them two more. Well, if you work backwards, he now takes 2 apples, right? Instead of giving 2, he gets 2 apples, and then instead of cutting his apples in half, he doubles them. So now if we just kind of unroll the mathematics, do the opposite of all the mathematics as far as adding 2 and then doubling, i.e. multiplying by 2, we should be able to work backwards from 1 and figure out how many he had. Well, he started with 1, so give him those 2 back. Now he has 3. Double it. Now he has 6. So that means he had 6 apples when he came to the last watchman. And if you now think about running the video forward now, he has 6. He walks up to the watchman. Oh, I got to give you half. Here's 3. Now I'm left with 3. I got to give you 2 more. Now I have 1. Yeah, he left with 1. That works, right? We just checked our answer as we went. Okay, now we just have to write down what we're doing so we don't make any mistakes and work it through all 3 watchmen. So we already did the first one. He's got 6. Then we run the tape backwards, right? We reverse the video again. He comes up to the second guy. He's got 6 apples at the end, but instead of giving 2, he gets those 2 back. Now he's got 8. He doubles it. That gives him 16. Then we work that backwards. The first guy, he's got the 16, gets 2 more. That's 18. Doubles it. That's 36. And he started with 36 apples. And if you work it forward, now take 36, cut it in half. That's 18. Take 2 away. That's 16. Go to the next guy, 16, cut it in half. That's 8. Give 2 more away. That's 6, right? And then we already know that 6 down to 1 works. So here's the math that we just figured out, that if we work 36 the right way, right, forward, we get back down to 1. So that's that last step of always checking our answer. So 36 works, right? The last step in Polya's process is to always make sure that everything is logical. You know, like if your answer came out to 40.5 apples, you'd think, all right, I must have screwed something up, because how can I have 40.5 apples, right? Or it came out to -3 apples, you'd be like, all right, something's not right. So just because you get an answer doesn't mean that it's the right answer. And this can happen quite frequently with certain types of word problems, especially ones that involve quadratics, parabolic shapes, projectile motion questions. A lot of times you'll solve those algebraically and you get 2 answers. One of them works in the context of the question and the other one doesn't. Often the second answer is negative and it just doesn't make sense, so you throw it away. So just keep that in mind, that sometimes the answer you get doesn't work in the context of the question. All right, here's another example. This one uses guess and test, where we have to arrange the numbers 1 through 6 in the circles of this triangle such that the sum along each side is 12. Well, you just jump in and start putting numbers in and see what works and what doesn't work. And how do we know that guess and test is the best way to do this? Well, there's not really much else we can do. There's really no math here. There's no hidden equation. We can't set something equal to something. We can't really draw a picture because the picture's already there. I mean, we can draw a picture, but it doesn't really help us figure out what's going on. We can't work backwards, right? Guessing and testing is kind of the only one that works here. So just start throwing some numbers in there and see what works. Your first guess is you start with 5, and then you go, okay, I'm going to put a 6 next to it, which gives me a 1. And then on the other direction, I put a 4 there, and then that leaves me with 3. So I got 12 on those 2, but the last one only adds up to 6, and well, that doesn't work. So then you realize, okay, the pattern of having big numbers and then ending with a small, big number and ending with a small, so that this whole side has smalls, all smalls, right, isn't going to work if they all have to add the same. You realize that the pattern is each edge, right, has to have a big and a small, right? You can't have all the smalls on one edge. So you could try just moving things around, like swap places with this, 6 and 1. It still adds up to 12, and then 6, 7, 8, 9, 10, 11. Ooh, that's close. So swap these two, right? This is still 12, and now you've got 12 on that one. So there's a guess and check. And this is just talking about the same thing. And here's our solution, right? Okay, now that you've kind of done the guess and check with the triangle question, now we can try it with the magic square, although you really don't have to guess and check with this one if you use a little logic. And that's as much as I'm going to say right now. Go ahead and read the question, pause the video, try it yourself, and then come back and make sure you get the right answer. All right, welcome back. I hope you figured it out that because we know that the rows, columns, and diagonals all have to add up to the same thing, they gave us the answer because this diagonal has 3 numbers in it, so we know they all have to add up to whatever that sum is. And once you add that up, it tells you how much you have to put in each of the remaining ones, right? You know this number because they already give us 2. You know this number because they already gave us 2. You know this number because they already gave us 2. The only one you don't know right off the bat is the 2, but once you get 37 from this column, then you know that 2 has to go there. And that's basically how Sudokus work. All right, how about solving a simpler example? This is a very useful tool that's used a lot in math, not just word problems, but calculus and physics and a lot of sciences. You solve something by solving a simpler example and then kind of generalizing that up to the more difficult question. So for this particular question, they ask us to add up the numbers 1 through 1,000, and you don't want to have to start doing that because that's a lot of work. That's 1,000 numbers to add together. So maybe try something a little bit easier, like the numbers 1 through 10. And you see that when you add up 1 through 10, you get 55. Now, how is that going to help you? Well, I don't know. Look for some patterns. Well, 55 is what? It's 5 times 11. Well, all right. So that means I have to have 5 pairs of 11. And sure enough, if you look at the numbers, 1 plus 10 is 11. 2 plus 9 is 11. 3 plus 8 is 11, and so on and so forth. There's actually 5 pairs of 11 there. And you go, wow, that's a pretty cool pattern. I wonder if that always works. Sure. Try, 1 through 20 if you want. You'll see that it works. 1 plus 20 is 21. 2 plus 19 is 21, right? 3 plus 18 is 21. It works. Well, what if I wanted to go 1 through 11, right? It wasn't an even number of things, so I won't have all these pairs. When I get down to the middle, I'll just have one number in the middle. Well, that takes a slightly different thing, and there is an actual formula for adding up 1 through n many things, and it works for whether you have an even number like 1 through 10 or 1 through 1,000, or an odd number. But we don't need to worry about that because the question we're asked is 1 through 1,000. So we only have to deal with the even case. So we don't have to worry about coming up with the more generalized question or an answer. We just have to solve this one. So if this pattern holds, we should be able to apply it to 1 through 1,000. So you write out just a few of them just to kind of recognize the pattern that you got 1 plus 1,000, right? 2 plus 999, 3 plus 998, and so on and so forth. Well, those all add up to 1,001. So the pattern is still holding. And then you got to ask yourself, okay, well, if we have all these pairs, how many total pairs are we going to have? Well, duh. When we had 10 numbers, 1 through 10, we had 5 pairs because you pair them up, right? So you're basically dividing by 2. And when you have 1,000 numbers, 1 through 1,000, you pair them up, you're going to have 500 pairs. So 500 times 1,001 tells you that if you add up the numbers 1 through 1,000, you get 500,500. And then you look back and ask yourself, does this make sense? Well, that's a pretty big number. It makes sense that it should be a big number. The patterns seem to hold. So I'm pretty confident that I got it right. Okay, how about another example, finding a pattern? Your uncle gives you $1 on the day you were born, $2 on your first birthday, $4 on your second birthday, and so on, basically doubling the amount on each birthday, and they want to know how much money does he give you on your 18th birthday. Well, if you didn't have the example 4, find a pattern up there, and you were just faced with this question, you could just start listing out the numbers. This is how much I get on when I'm born, on my first birthday, second birthday, and so on and so forth. But how do you even know what you get on your third birthday if you don't already see the pattern? Well, it doubles, right? $1, $2, $4, $8, 16, 32, 64, and so on and so forth. So you could just write those all out until you get to the 18th. And then that's how much money you would get on the 18th. So you don't even have to worry so much about the math. As far as once you see the pattern, then you can just write it all out. 18 is not that many to write out. But if they asked how much money would he give you on your 81st birthday, well, now that's a big pain in the butt to have to list out 81 of them. So it would be much nicer if you could come up with a generalized pattern that would help you. And if you watched my Thinking Mathematically video, you would know that there's a nice simple pattern to this, because if it's doubling, right, it's basically powers of 2, and you can figure that out easily. Well, like I said, we can just write them out, or we can look for the pattern that when you're born, you're 0 years old, and you got $1, which is 2 to the 0th power. On your first birthday, you're 1 years old, you got $2, and that's 2 to the 1. On your second birthday, 2 squared is 4. Aha, now I'm seeing the pattern. He's always giving me 2 to the n dollars. So on my 18th birthday, it's 2 to the nth. And when you do 2 to the 18th, he's going to give you $262,144. And you're going to go, that is one heck of an awesome uncle. All right. Now, we need to determine if the answer makes sense and is feasible. Have we committed any math errors? Because at first glance, that number might seem way too big to you, but that's the beauty of exponential growth. It does actually get big really, really quick. And so you could try it with some other numbers and see that if you start with 100 and then double and double and double and double, you can see that it gets really big really quick, and you go, all right, now you can see that these numbers grow really fast, and the number that you got, even though it's so huge, is probably correct, and in fact, it is. All right. Don't look at the bottom. Try a skill check again. Suppose you spend $20 every minute for every day for a year. How much money would you spend in 365 days? How would we figure that out? Well, again, isn't that kind of a pattern question where, so how would you tackle this one? Well, you'd have to see that there's a pattern to it. You know, $20 every minute for every day for a year. You just got to figure out how many minutes there are in a year and then multiply that by $20. So we've got 365 days times 24 hours, right? And then in each hour, there are 60 minutes. That's going to give us a total number of minutes, and then multiply that by 20. And that's how you get the answer. Pretty simple. All right, drawing a diagram. A baseball league is forming in which each of the teams will play 4 games against each of the other teams. There are 5 teams in the league. There's their names. Determine how many total games will be played. Well, if you understand the problem, it means you have to realize that each team plays the other 4 teams, right? And once you figure that out, it's just a matter of kind of drawing a picture or a diagram or writing it out so that you can be systematic to make sure that you have all the pairings of each team without thinking of them twice or forgetting any of the other ones. So we realize that when the Raiders play the Blazers, it's the same thing as the Blazers playing the Raiders. That's what I mean by we don't want to count them twice. So start with a picture and go, here are my 5 teams. And this diagram shows the Raiders playing everybody. And that's 4 games. And now we're done with the Raiders because the Raiders have played everybody. So now when we go to the Blazers and figure out, okay, how many more games do the Blazers have to play in order to play everybody? They've already played the Raiders, so we don't need those. So we just need Eagles, Jackals, right? Wouldn't you hate to be the Jackals? And Warriors. And now we're done with both Raiders and Blazers. We had 4 from the Raiders and the 3 more from the Blazers. Okay, now we move on to the Eagles. Well, they've already played the Raiders, they've already played the Blazers, so now all we have is Jackals and Warriors, which adds 2 more. And then we move on to the last team, the Jackals, which have played everybody but the Warriors, which adds 1 more, and 4 plus 3 plus 2 plus 1 gives us a grand total of 10 lines or 10 games. Now, the original question said each team will play 4 games against each of the other teams. So we kind of used two techniques here. We solved for a simpler one. Instead of thinking of 4 games each, we just thought of it as playing 1 game each, and then we can expand that to 4. And after we used the diagram, we figured out there were 10 of these pairings, but each of those pairings represented 4 games, so it was a total of 40 games. All right, our next example. How many ways can you make change for 50 cents out of quarters, dimes, or nickels? Make a list, guess and check, or guess and test, if you want to call it that, would also work. Because really, again, there's really no math to do here. It's just a matter of brute force, writing out all the different combinations. Start with, okay, if it's just quarters, it's 2 quarters. If it's just dimes, it's 5 dimes. If it's just nickels, it's 10 nickels. Okay, now let's combine things. Okay, 1 quarter, 25 cents. Now how many dimes? 2 dimes, and what's left? 1 nickel. Or how about 1 quarter and then all nickels? You can see that what I'm doing is I'm systematically working through all the coins. Start with all quarters, 2 of them, and then go to all dimes and all nickels. Take care of those. Those are simple and easy. Now go to 1 quarter and then the maximum number of dimes. So 1 quarter, 2 dimes, and that leaves me with 1 nickel. Now go 1 quarter, 1 dime, and then I need 3 nickels. Okay, then 1 quarter, no dimes, and I need 5 nickels. And I've come up with all the possible ways of doing it. And that's where making a list helps, is it keeps you on track as far as, if I start with 2 quarters, I don't do any of these. I can also do 1 quarter, and the most I can have for dimes is 2, because 3 of them would be 30 cents, and that would have 55 total cents. That doesn't work. And then that leaves me with 1. And then I stay with 1, drop this down to 1, drop this up to 3. Stay with 1, drop this down to 0. That's got to go to 5. Now I'm done with all my quarters. So now I'm going to go 0 quarters and then go maximum number of dimes, 5, which leaves me 0 that. Then 4, which leaves me 2. 3, which leaves me 4. You see how the pattern is that you start with a maximum of one thing and then work your way down. And it's always best to start with the largest thing first, quarters, then dimes, then nickels. But we could have done it in any order, and we still would have got the same list, just it would have been rearranged. So being able to make this kind of list is very helpful, especially when it comes to dealing with probability questions, if you ever have to study probability and you have to figure out the number of ways you can do something. So it looks like 9 combinations was the most we could do. Let's look at our last example. If a number is multiplied by 8 and the product is added to 6, if the sum is 30, what is the number? Aha. Well, this is a great example of using a variable, because this is a question that actually gives us some information that we can translate from English into math. If the sum is 30, something is 30 means something equals 30. That means the sum equals 30. There's an equation. And when we have an equation, we can solve things. We just plug in for our unknowns. Well, a number is multiplied by 8. We don't know what that number is. So whenever we see a number or something like that, we think x. X is multiplied by 8. So we multiply that by 8. And then the product is added to 6. We give 6 to that. And then it says if the sum is 30, so all of this stuff is 30. And all we have to do is solve for x. This is really easy. 8x plus 6 equals 30. We subtract the 6 and say 8x equals 24. Divide by 8, and x equals 3. It's that simple, right? And then we look back and make sure it makes sense. Take 3, multiply it by 8, add 6 to it, and go, yep, we get 30. Okay, your last skill check. See if you can find the sum of 3 consecutive odd natural numbers is 39. Find those 3 numbers. Well, you could do it by guess and check. You could do it with a pattern, right? We know that the sum of 3 consecutive odd numbers. If this is my first number, then wouldn't the second number be x plus 2? Because it's, if we have an odd number, we add another odd number to it. So 9 up to 11 is 2 more, and so on and so forth. And then the next one would be plus x plus 4. And that whole thing has to equal 39. And you go, well, that's 3x plus 6 equals 39. 3x equals 33, x equals 11. And as I set it up, right, this was my first odd. The second number would be 11 plus 2, which is 13, and then 15. But you also could have done it with guessing and checking, the sum of 3 consecutive odd numbers. You could have started with a 9, 9, 11, and 13, and saw that that was too small. So you go, okay, well, how about 15, 17, and 19? That's too big, so you know it's somewhere in between. So then you try 13, 15, and 17. Nope, 11, 13, 15. You go, aha, it works, right? So guessing and checking would have worked as well. Now, in summary, we saw how to solve a bunch of different things using different tools. Let me try and generalize Polya's steps for you, because I know his steps can seem a little complicated. I have a similar set of steps. Whenever I'm faced with a word problem, this is how I tackle it. I read it through. And when I read it through, all I'm looking for is the theme. What kind of question is it? Because remember I was telling you how all of these things kind of fit in families of questions. So is this a question that's dealing with distance equals rate times time? Is it a mixture question? Is it a geometry question? And there's a few other as well. So I'm going to read it all the way through and just kind of get the theme. Then I'm going to reread it. And when I reread it, all I'm trying to identify is what is the question? So find the question, i.e. what am I trying to solve for? Because that tells me where my variable goes, if there is one, because we saw some of these really didn't have those. I draw a picture whenever I can, and I assign variables. It's that type of question, right? So you're going to reread it in small little bite-sized pieces, and you're going to do all these things. You're going to assign variables, you're going to translate English into math, you're going to draw a picture, you're going to identify what the question is. Step 3 is the biggie. This is where you have to either create or find the hidden equation. And what I mean by hidden is, now, a lot of the examples we saw today didn't have equations, but most of the word problems you're going to be presented with in your academic career are going to involve some sort of equation. You're going to have to solve for x or p or y or q or z or whatever it happens to be. Well, in order to solve for those variables, you have to first come up with an equation so that you can solve it. Well, they're not going to just give you an equation. That would be too easy. You're going to have to create it from the information they give you. So you always have to find the hidden equation or create the hidden equation based on the information you give you. Sometimes it's just as simple as taking the English and translating it into math, and that's how you find the hidden equation. Or sometimes you have to create it. They give you a bunch of information, and you have to kind of set up the equation on your own. But 3 is the biggie. Come up with that equation. 4 is the easy one. Solve it. And then 5, check your answer, make sure it works both mathematically and it also makes sense in the context of the question. Because like I said, especially with quadratics, you can oftentimes get a secondary answer that mathematically is correct, but does not fit in the context of the question. You know, like 22.3 apples wouldn't make sense. Those types of things. All right, guys, I hope this helps.